The first example that we always do with Ampere's law, and it's the one that you really have to practice until you can do it cold, because it shows up all over the place, not only in these examples, but in the next chapter's examples too, is the infinite, or nearly infinite, the very long current carrying wire. What I've drawn here is a current moving in the positive x direction, and I've already drawn the magnetic field lines that surround the wire. You'll recall that we could do this just from a quick right-hand rule, or if you wanted to, you could sit down with the Biot-Savart law and figure that out for yourself. But I don't know about you, I'm ready to move on from Biot-Savart. This diagram shows the exact same situation, but with all of the coordinate axes just turned 90 degrees, so that the z-axis now points this way, and the current is pointing into the page. You'll see why that's useful in a minute. You'll remember from Gauss's theorem that one of the important things to do was to choose a so-called Gaussian surface that would take advantage of the symmetry exhibited by the field lines. In the case of almost all the Gaussian examples, because the field lines were poking out in all directions, you would choose some three-dimensional closed surface that would have a similar kind of effect, a similar kind of symmetry. Here, we want to look for what are called Amperian loops, which serve the same purpose in Ampere's law that Gaussian surfaces did in Gauss's law. What you want to do is choose a loop that has the kind of geometry to it that matches the geometry of your setup. So if you look at this diagram here, you can see very clearly that choosing an Amperian loop that was a circle would be a really clever choice in this case, because a circle would have the same sort of vector pointing that the current elements, the magnetic field elements have for that wire. The magnetic field moves around in circular loops, so we choose a ds path that will also have that same kind of circular curve to it. If you'd like, you can imagine a bunch of ds vectors all kind of going like this. And ending up in a circle. So, we begin with this rather complicated looking integral of B field dotted with ds vectors. And the first thing we can take advantage of is that the B field lines and the ds vectors are always parallel. This allows us to do two things at once. It allows us to get rid of the dot product, because we've already chosen an Amperian loop where the field and the ds are parallel, so the dot product goes away. And we also can get rid of the vector nature of both of these expressions. The next thing that's nice about this is that because of the way these field lines look, you'll notice that they loop around at a constant distance away from the wire. This is a reminder that the magnetic field strength drops with distance. So if our path is always at the same distance away from the center wire, then that means that the B field is going to have constant magnitude everywhere along this Amperian loop. And here, of course, loop means this guy right here. And finally, we note that this loop is simply a circle. This makes Ampere's law turn into something very, very simple. We have the circumference of the Amperian loop, 2 pi r, multiplied by the constant field strength at that particular distance r, equals mu naught times the enclosed current. In this case, of course, the enclosed current is just given as I. So this leaves us finally with mu naught times I over 2 pi r. And that's it. You'll recall that the Biot-Savart method for getting this result was pretty painful, and it took a long time. Using Ampere's law, we got there with just a couple lines of work. You will find that knowing the magnetic field for a long straight wire is going to come in handy more times than you can really anticipate. So really make sure that you're good at this. Don't just memorize it. Although memorizing this expression is a good idea, don't just memorize it. Practice this method until you can knock it out cold, because I've seen lots of examples on AP exams where the first step in a multiple part problem is to figure out the magnetic field from a long straight wire. And there's usually points for just using Ampere's law to get this answer.